Hey everyone, and welcome. Today, we're going to go on a pretty cool scientific journey. We're going to see how electricity can do some amazing things when it passes through liquids. We're talking about the science that connects a simple lemon to the super shiny chrome on a car. So, let's dive right in.
Let's kick things off with a little mystery you've probably seen 100 times. You know that brilliant mirror-like shine on a new bike's handlebars? Well, what is that? I mean, if you were to scratch it, you'd find a totally different, kind of dull metal underneath. It's definitely not paint, it's something way cooler. And it's all about science.
All right, first things first. Before we can solve our shiny handlebar mystery, we've got to figure out which liquids can even carry electricity in the first place. Think of it like a road for electricity. Some liquids are like a superhighway, and others are a total dead end. So let's head over to our virtual lab and put some to the test.
Now you might think all water conducts electricity, right? Well, that's actually a bit of a trick question. See, super pure distilled water is a terrible conductor. It's like that road is completely blocked. But the second you dissolve something like salt in it, bam! A brand new highway opens up and that electric current can just zoom right through. This is exactly why your tap water can conduct electricity. It's already got tiny bits of mineral salts dissolved in it.
And you know what? It's the same story for a lot of stuff you'd find right in your kitchen. Liquids that are solutions of acids, bases, or salts, they're usually fantastic conductors. That's why something acidic like lemon juice lets electricity pass through with no problem. But then you have other liquids, like, say, vegetable oil, and they just don't have what it takes. They basically slam the door on the electric current.
But here's the thing, not all conductors are created equal. Some are just better at it than others. In this experiment, some students hooked up a light bulb and saw that it glowed way brighter with lemon juice than it did with regular tap water. So what does that tell us? Well, a brighter bulb means more electricity is flowing. That means lemon juice is a much better conductor than tap water is. Simple as that.
Okay, so we know electricity can flow through certain liquids. Got it. But this is where things get really interesting. See, the electricity doesn't just quietly pass through these liquids. Oh no, it actually gets in there and starts mixing things up, causing some real changes. Let's take a look.
This right here is the big idea for today. A chemical effect just means that the electricity is causing a real chemical change. The liquid literally isn't the same after the current has passed through it. The electricity isn't just a visitor, it's an active ingredient making new things happen.
And the coolest part is, you can actually see the science happening with your own eyes. These are the clues you gotta look for. If you pass a current through a solution, you might see tiny bubbles of gas forming on the metal rods. We call those electrodes. Or you might see the color of the whole solution change. Or maybe even a thin layer of metal starts to form on one of the electrodes. All of these are signs that chemistry is in action.
All right, now let's circle all the way back to our bicycle mystery. The secret to that super shiny handlebar is a process that uses these chemical effects we've been talking about. It's called electroplating. And trust me, this is where the real magic happens.
So, electroplating is probably one of the most useful ways we use chemical effects. The easiest way to think about it is like this. You're using electricity as a microscopic paintbrush. You can take an object made of a cheaper or stronger metal and just paint a super thin, perfect layer of a different metal right on top of it, like shiny chromium or even valuable gold.
So how does it actually work? Well, it's kind of like following a recipe. First, you start with a solution that has the metal you want to use for painting. In this case, copper from copper sulfate. When you pass an electric current through that solution, the electricity actually breaks the copper sulfate apart. The now free copper gets pulled toward the electrode that's connected to the negative end of the battery. And it sticks to it, forming a perfect thin coating. How cool is that?
Seriously, once you know what electroplating is, you start seeing it absolutely everywhere. That shiny chromium on car parts and your bath taps? Yep, that's electroplating. It resists scratches and it doesn't rust. The tin coating inside food cans? That's electroplating too. It keeps the iron of the can from touching your food. And that affordable jewelry that looks just like real gold? It's usually a much cheaper metal with a tiny layer of gold electroplated right on top.
But electroplating isn't just about making things look pretty. It has some really important jobs. Iron is super strong, right? We use it for huge things like bridges and cars. But it rusts like crazy. So by electroplating a thin layer of zinc onto the iron, we create this amazing protective shield. The zinc basically rusts instead of the iron, which keeps the important structure safe and strong for a much longer time.
Now, this is a really powerful process, but you know what they say? With great science comes great responsibility. Anytime we're working with electricity and chemicals, we have to be smart and, most importantly, safe.
So this shows us the other side of the coin. Those conducting solutions that are used in big electroplating factories, they're full of chemicals. And after they've been used, they become a kind of pollution. You absolutely can't just pour this stuff down the drain.
Look, protecting our environment is just as important as doing the science experiment itself. That's why there are very specific rules and guidelines for how to get rid of these chemical wastes safely. Following the rules from our local authorities is how we protect our rivers, our soil, and our whole community.
All right, class, you've learned a ton, so I think it's time for a little pop quiz to see what you remember. Let's test that knowledge. Don't worry, no pressure.
Okay, first question. Think back to the beginning of our lesson. What does a liquid need to have in it to conduct electricity? Remember, it needs those dissolved salts, acids, or bases. So, which one of these doesn't have that?
That's right. The answer is C. Sugar will dissolve in pure water, sure, but it doesn't create those charged particles that electricity needs to travel. So, a sugar solution in distilled water will not conduct electricity. Awesome job!
Let's do one more. We were just talking about this one. What's the main reason, the most important reason for putting a zinc coating on something big and strong that's made of iron?
Exactly. This is the perfect example of the protective power of electroplating. That zinc layer acts like a shield. It sacrifices itself to the rain and the weather, all to keep the iron underneath from corroding and rusting away.
And that's our look at the chemical effects of electric current. From making things shiny and new to protecting massive structures from falling apart, it's a crazy useful process. So it makes you think, right? With this amazing ability to literally paint with metal, what new inventions or amazing solutions could we create with this technology in the future? Thanks for joining me today.